Electronic Control and Digital Electronics Level 3. Module 3, Session 3.1. Session 3.1 will cover the following content: Operational Amplifiers, Subject Outcome 1.7. We are now going to discuss the operation of operational amplifiers in a bit more detail. Operational amplifiers are more commonly referred to as op-amps. The two most common types of amplifier are 8-pin and 14-pin. Many op-amp circuits use balanced power supplies. A balanced power supply has two equal voltages, one positive, typically 9 volts, and the other typically negative 9 volts. Other op-amps use unbalanced supplies, with their negative supply grounded. The ideal op-amp displays the following ideal characteristics: infinite open loop gain, infinite input resistance, infinite bandwidth, output voltage is 0 when the input voltage is 0, output resistance is 0. Transfer characteristics. This graph is a typical voltage characteristic of how the output voltage varies as the differential input voltage is varied. This is called a voltage sweep. From the graph, you can see that the output is directly proportional to the input for only the small range of AOB. This is where the op-amp behaves linearly and there is minimum distortion. Outside this range, the inputs will cause saturation. Op-amps have many uses which can be configured by creating various circuits around the device. These include the inverting amp, non-inverting amp, voltage follower, voltage adder, integrator, differentiator, audio amp. The inverting amplifier. The ideal op-amp has an infinite resistance between the two inputs. It can thus be considered an open circuit. Therefore, the current flowing into the op-amp for all practical purposes equals 0. The output voltage for the circuit is given by Vout is equal to minus Rf over Ri multiplied by Vin. The minus sign indicates that the output is 180 degrees out of phase with the input signal. Inverting circuits are used as DC amplifiers, comparators in power supplies, in detector circuits of transducers, and for amplifying small signals. The inverting circuit is also used as a summer or an adder, which will be discussed later. The non-inverting amplifier. This is also a DC amplifier, but it has the advantage of higher input impedance. The output voltage for the circuit is given by Vout is equal to 1 plus Rf over Ri multiplied by Vin. A useful application of the non-inverting circuit is that of the voltage follower. All the other applications for the inverting op-amp also applicable for the non-inverting op-amp, except for the adder. The voltage follower. This circuit uses 100% feedback, therefore Vout equals Vin. Since the op-amp has a high input and a low output impedance, a voltage follower can be used to match impedances. It can also be used as a buffer between two stages to protect the output of the first stage. The low output impedance means that a large output current can be drawn while the input draws almost no current. The gain of this type of amplifier is unity, or 1. The voltage adder. The output voltage for this circuit is given the following equation. The overall gain of the circuit is set by the feedback resistance. The gains of the individual inputs are then scaled independently by the relative input resistances. It is used in analog computers and is also often used as a signal mixer in audio equipment. The voltage integrator. The integrator performs the mathematical operation of integration, which finds the area under the curve generated by the input waveform. The output voltage for the integrator is equal to the integral of the input waveform divided by the RC time constant. The negative sign shows the inversion resulting from using the inverting input of the op-amp. The integrator is also used for wave shaping. The circuit shows the basic integrator circuit with the input through a resistor to the inverted input. The feedback component is now a capacitor. The voltage over the capacitor is the capacitance divided by the charge. The voltage differentiator. Differentiation is the process of finding instantaneous rates of change. This is done by finding the gradient of a line tangent to a point of interest on a graph. Differentiators are used in analog computers, wave shaping, and power regulation. Different input waveforms behave differently at the output. The sine wave gives a cosine at the output, whereas a cosine at the input produces a minus sine wave at the output. The square wave produces a bipolar train of sharp pulses, while a sawtooth input produces a square wave at the output of the amp. The audio amplifier. The audio amplifier uses only one power supply lead, working in the inverting mode with negative feedback and coupling capacitors. The voltage divider circuit, consisting of R1 and R2, makes it possible to work from one supply line. The coupling capacitors can be calculated using these two equations. F is the lowest operating frequency in the audio spectrum, which is generally accepted as 30 Hz. The gain is still RF over RI. The audio amplifier is used in high, low, and band-pass filter circuits, volume control in hi-fi systems, and tone controls. Let's now watch a video of a small audio amplifier circuit in action.
Today we want to talk a little bit about the operational amplifier, better known as the op-amp. As you are aware, the op-amp can be used for various applications. For example, non-inverting amplifier, inverting amplifier, summing amplifier, the one you'd use in a calculator to do addition, etc. And as a comparator, where you can compare two inputs and get one final output, which is normally used in equipment like battery chargers or smart battery chargers. And then you can also use it as an audio amplifier. In this particular instance, we are using the LM386, which is a very cheap integrated circuit. The N/4 is ideal for audio. You do get them N/1, 2, and 3, but the 4 gives you lovely bass notes. I'm now going to put it on so you can hear the audio coming through from these speakers. I'm going to plug in my cell phone and listen to some music and then talk to you a little bit about the components that we have used here. That's an audio amplifier. There's a few things I'd like to point out here. First of all, notice that I've used quite a high value capacitor here at the output. You've learnt of RC coupling in amplifiers. You've learnt of transformer coupling. You've also learnt of direct coupling. This is a method of coupling the speaker with your output, which comes from pin 5. Notice also it's quite a high value. The reason for that is to get lovely bass sounds coming through to your speaker. If you use a lower value, like say a 450 microfarads or 100 microfarads, you will find that the higher frequency notes will be more predominant than the bass notes, and it's not actually ideal for listening insofar as music is concerned. Another important factor that one needs to consider is this capacitor here, which must not be left out. It's 100 nanofarads or a 0.1 microfarad. It actually decouples all interference or outside frequencies that may creep into your input, which is here. It filters it down. So that's another example of a high pass filter, something that you've learned about already.
End of the video. We'll be right back.